Hello. So we're going to look at another application of similar triangles, and this is actually my favorite one because it involves right triangles, and it's actually really cool. So let's say you have a right triangle drawn. Well, if I go from the vertex that is the right angle and draw an altitude, meaning I go from the vertex straight down to the hypotenuse, forming a right angle, I actually create three similar triangles. The first one is the right triangle as it was to begin with. The second one is using two of the points and the point of intersection to the hypotenuse. And the third one is using the two other points and the point of intersection to the hypotenuse. So in essence here, what is drawn, I have triangle ABC being similar. Notice how that looks kind of like the congruent symbol, except it doesn't have the equals underneath. So it's similar to triangle ABC is similar to triangle ADB. So ABC is similar to ADB, and triangle BCD is also going to be similar to ABC. So what does that mean? That means if I have a right triangle and I know two of the sides, I now know automatically, if I were to draw an altitude here, I know the measure of this altitude. I know the measure of the two sides, how they would be split. I also know the hypotenuse as a whole. I know so much just using, honestly, the principles of similar triangles in the Pythagorean Theorem. And that's why I love this. Love this application because it's very quick and simple actually to see and to come up with. So let's take a look here. It actually also proves and is a great segue into something that we'll talk about next. Because the ultimate thing about right triangles is that there are these similarities that you see constantly, and there's these relationships between similar triangles so often that if we know the angle measurement, and we know one of the side lengths, we should know everything else automatically. Or if we know two side lengths, we should automatically know what the angle measurements are and the other side lengths. And this all has to do with what's called trigonometric ratios, which we'll look at in the future. But this is kind of a way to prove that. So I'm going to erase this then, and we're going to get started. So hopefully you paused and got that beforehand. If not, you can rewind, copy that down, and copy down the triangle. So let's start off with the fact we know that this side BC is 30, and we know that A to B is 40. Well, if we know that, we should be able to find AC very quickly using the Pythagorean Theorem. So if we use the Pythagorean Theorem, meaning that the square of the hypotenuse, so what AC is going to be equal to the square of that's going to be equal to the sum of the square of the legs, so 30 squared plus 40 squared. We'll end up seeing that we get 900 plus 1600. And so we get 2,500. And we take the square root of both sides here. We end up AC is equal to 50. So that's just using the Pythagorean Theorem. As we see 30 and 40, and some of you are probably saying, isn't that like 3, 4, 5? It is. We just made a similar triangle with 3, 4, 5 by multiplying it by 10. That's pretty cool, right? So if you know those Pythagorean triples and you recognize that this is also just the same thing as just multiplied by a factor, you automatically know what the other side is. So that's why it's cool to start taking note of those Pythagorean triples, especially for those of you that are doing construction and other machine work, because a lot of times right angles come up a lot and right triangles come up a lot. So you start recognizing these patterns quite often. So anyway, in that regards, AC is in total length 50. So we at least know that. So if you need to pause down the work for the Pythagorean Theorem to find AC, go ahead and pause now and copy it down. Okay, I'm going to erase it now. So AC is 50. We know that now for a fact, that AC in total, the length is 50. So this whole thing here should be 50. Okay, but we're going to want to find AD and DC and also BD. Well, how are we going to do that? We're going to use the fact that these triangles, this right triangle drawn with the altitude from the right angle to the hypotenuse, form similar triangles. Okay, So as we said before, ABC is similar, and I'll write that again up here. Triangle ABC is going to be similar to, let's start up here. Triangle A, D, and then B. Triangle ADB. Okay? Well, how do I know that? Well, I know that A is going to be the same angle as A. I know that B was a right triangle, and D is the right triangle here, so therefore C must be similar to B then, the new B, so this one that's right here. Okay, not the whole right angle, just this portion here. Okay? All right, so if I know that fact, what else do I know? Well, I know that sometimes it's actually easier for most people to draw out the triangle again. So we had ABC. So ABC was 30, 40, and 50. And what we have over here is ADB. And the only thing we know is that AB is 40. So that was ABC, and this is ADB. Okay? So the only thing we have in relation to one another here, and I can put these ADB, that makes it easier for you. This was C, that was B, and that was A. So you can see the similarity between them. We know that there has to be a relationship between AC and AB because they're similar. And both of those are the hypotenuses. So what is that similarity between them? We're trying to find out what is BD and what's AD. Let's start by finding BD first. So if I want to know what BD is, I'll call that X. I know that AC, or this 50, has to be related to 40, and 30 has to be related to X. So if I wanted to set up a proportion for that, I could. I could say X over 30 has to equal 40 over 50. Because whatever factor we increase by should be the same. Okay, well, if I do that and I solve for X, how would I solve for X? Oh, I multiply both sides by 30. And if I multiply both sides by 30, I end up with X equals, I get 120 over 5, or I get 24. Okay? So we end up with X equaling 24. That's kind of cool. So we did know that BD has a measurement of 24. Well, we actually don't even have to use the fact they're similar triangles anymore, because this is a right triangle, and we know two sides. This is a right triangle, and we know two sides. So we can use Pythagorean Theorem to find the third side. But so you get more practice using the similar triangles, I'm going to solve it using similar triangles. Again, you can do the Pythagorean Theorem now to find the other side. Okay? So let's now, I'm going to erase the math we did here, because we're now looking for another side here. Let's find AD. So we know that this is 24. Let's find AD though. So I'll call it ADX. So we know that X has to relate to 40. 24 has to relate to 30. 40 has to relate to 50. Does it matter which one I use? No, I'm going to stick to what was given to me to begin with though, the 40 and the 50. Okay, so X relates to 40 the same way that 40 relates to 50, because they have to be directly proportional. All right, now, how do I solve for X? Okay, well, to solve for X, what I would do is I would multiply both sides by 40. Okay, and when I do that, I end up with X equaling, now it'll be 1600 divided by 50, or 160 divided by 50, and I get 32. So AD has to be 32. All right, cool. So all we have to do now is find DC. So we can use Pythagorean Theorem. We could use similar triangles. Or, wait, there's a third thing we can do now. I know that this whole thing's 50. I know that this part's 32. How much would the rest of it have to be? That's right, we could just subtract. 50 minus 32 will give us 18. And I have now taken a right triangle, drawn an altitude, and found out the length of the altitude, what the new lengths of my pieces of the hypotenuse would be by splitting it, all from the fact that I just had a right triangle and I knew two of the sides. Look how powerful that is. Just knowing the fact that if I draw an altitude from the right angle to the hypotenuse, I have three similar triangles. I know the Pythagorean Theorem and how to use it. And so given two sides and drawing that altitude, I automatically know everything else I need to for this. That's crazy. It's not just crazy, it's wonderful. It's beautiful. So because of that, if I had to, let's say I had this right triangle here, and I needed to, I wanted to cut smaller size pieces, or take that right triangle and cut it into smaller size pieces that could be models, for instance. They could be models for scales. Well, all I have to do is go from the vertex directly to this other side so it forms a right angle, because I automatically would create two more similar triangles that I could then use for modeling something if I wanted to. That's awesome. So that's actually how this is used a lot. So a lot of times what people will do is they'll create the altitude to make these similar triangles. For cutting, so that they can cut, so they can get a smaller scale version of what they had previously, because they will. It'll always be it'll always be the one that starts off with the larger angle that will give that to you. It will always give you the smaller triangles, smaller similar triangle. And so sometimes people do that. Other times, whenever people are building, they'll have an extra 2x4 go here for the altitude. It gives it more stability in case you need to add more weight on it. So this is why this is important to know. It's something really. It's honestly, I just love it because it's beautiful mathematics. It combines similar triangles, combines the idea of the Pythagorean theorem, and as I said before, it also segues into understanding that because for any right triangle, these similarities have to hold. That means if I had a 3, 4, 5, this would hold as well. That means I could take a 3, 4, 5 divided by 10, because 30 divided by 10 will give us 3, 40 divided by 10 will give us 4, 50 divided by 10 will give us 5. So we get the 3, 4, 5. That means automatically this would be 2.4, this would be 1.8, this would be 3.2. I could double these and do the same thing. I know automatically. But that means that these angles have to stay proportional to that the entire time, because they're the only thing that's not changing. The lengths are changing, but the angles stay the same. So therefore, there must be a special relationship with angles in the side of triangles, which we've already talked about before, but even more so with right triangles. So if I automatically know the measurement of an angle, I can find out what this relationship has to be regardless. And that's called trigonometric ratios. And we'll see them soon.